A single molecule just performed 5 different jobs: memory, logic gate, analog processor, electronic synapse, and selector switch, all without changing its physical structure. Silicon can't do even 2 of those.
A team at the Indian Institute of Science in Bangalore just published a study showing molecular devices that can dynamically reconfigure their function based on how you stimulate them. And this isn't a lab curiosity, this is a potential replacement for silicon that could fundamentally change how we build computers, AI hardware, and everything electronic.
Okay, but people have been saying silicon is dying for decades. Moore's law is supposedly over. What's different this time?
Fair pushback. Let's start with why silicon actually is hitting a wall. Because it's not hype, it's physics. Moore's law predicted transistor counts would double roughly every 2 years. For 50 years that held up, but we're now at transistors that are about 3 nanometers across. That's roughly 15 atoms wide. You physically cannot shrink much further before quantum tunneling kicks in. Electrons just jump through the barriers instead of flowing through the intended pathways,
So it's not an engineering problem, it's a physics limit.
right? And the other wall is energy. Modern AI chips consume enormous power because every operation requires shuttling electrons through fixed circuits. Your GPU doesn't change what it is, it's hardwired. If you want it to do something different, you need to move data to a different part of the chip or to a different chip entirely. That data movement burns more energy than the actual computation.
Memory wall, power wall, physics wall, triple threat.
And molecular computing potentially addresses all three. The team at ISC, led by Assistant Professor Sritosh Goswami at the Center for Nanoscience and Engineering, built devices from 17 carefully designed ruthenium complexes. Ruthenium is a transition metal, element 44, on the periodic table. By adjusting the chemical groups attached to the ruthenium atom, called ligands, and changing the ionic environment around it, the same physical device exhibits completely different electrical behaviors.
When you say different behaviors, how different are we talking?
Night and day. In one configuration, the device acts as a digital memory cell, stores a 0 or a 1 and holds it, change the stimulation, and it becomes a logic gate, performs and or not operations. Change it again, and you get an analog processor that can handle continuous values, not just binary. Stimulate it differently, and it becomes an electronic synapse. It can strengthen or weaken its connections based on experience, like a neuron in your brain.
Wait, it learns?
That's what's wild. Pallavi Gower, the first author and PhD student on the study, said, and I'm quoting, with the right molecular chemistry and environment, a single device can store information, compute with it, or even learn and unlearn. That's not something you expect from solid state electronics.
Okay, I need to understand the mechanism. How does a molecule switch between being memory and being a logic gate?
It comes down to electron behavior at the molecular level. These ruthenium complexes can undergo oxidation and reduction, gaining or losing electrons in multiple stable states. When you apply different voltages or change the ionic environment, you shift which redox states the molecule occupies. Each state has different conductance properties. Some states give you sharp switching between high and low conductance. That's digital behavior, good for memory and logic. Other states give you gradual, continuous changes. That's analog behavior, good for synaptic learning.
So it's not that the molecule physically changes shape, it's that the electrons rearrange.
The electrons rearrange, the ions around the molecule shift, and the overall electronic structure changes. And here's what's critical. These aren't random changes. The team developed a theoretical framework based on many-body physics and quantum chemistry that can predict the device's behavior directly from the molecular structure. You design the molecule, and the theory tells you what it will do.
That's the part that's been missing from molecular electronics for 50 years, right?
For more than 50 years, scientists have known that individual molecules could theoretically function as electronic components. The idea goes back to a famous 1974 paper by Aviram and Ratner proposing a molecular rectifier, but the reality was brutal. Molecules in real devices don't behave like simple isolated components. They interact with each other, with the surfaces they sit on, with the electrodes. Tiny structural differences cause wildly nonlinear responses. The ISIS team cracked this by developing a transport model that accounts for all those interactions, how electrons move through the molecular film, how individual molecules oxidize and reduce, how countarions shift within the matrix. It's the first time anyone has had a predictive theory for multifunctional molecular devices.
So where does neuromorphic computing fit into this?
That's where it gets really exciting. Neuromorphic computing is the field trying to build hardware that works like a brain instead of like a traditional computer. Your brain doesn't separate memory and processing, every neuron does both simultaneously. It learns by changing the strength of connections, not by rewriting data in a separate memory bank.
And current neuromorphic chips are basically faking it?
Most of today's neuromorphic hardware uses oxide materials and something called filamentary switching. They're carefully engineered machines that imitate learning. The ISE team's molecular devices don't imitate learning. The learning is encoded directly into the chemistry. The molecule's own oxidation states are the memory. Its conductance changes are the computation. Its ability to strengthen and weaken responses is the learning. Chemistry becomes computation.
Sritosh Goswami said something about chemistry being an architect of computation, not just a supplier.
That was actually his colleague Sribrata Goswami, a visiting scientist at Senzi who led the chemical design, and that quote captures it perfectly. For decades, chemistry has supplied materials for computation silicon, germanium, gallium arsenide, but the computation happened in the engineered structure, the transistor layout, the circuit design. Here, the computation happens in the molecule itself.
What about scaling? A cool molecular device in a lab is one thing. Billions of them in a chip is another.
That's the honest challenge. The team is already working on integrating these molecular systems onto silicon chips, so it's not about replacing silicon overnight, it's about augmenting it. Imagine a hybrid chip where the silicon handles what it's good at fast, reliable digital logic, and molecular layers handle what silicon can't do adaptive learning, analog processing, dynamic reconfiguration, all at a fraction of the power.
What would that mean for AI?
Current AI hardware is brutally inefficient. Training GPT-4 consumed an estimated 50 gigawatt hours of electricity. Your brain runs on about 20 watts and outperforms these models at most real-world tasks. If you could build hardware where the computation, memory, and learning all happen in the same material at molecular scale, you could potentially cut AI energy consumption by orders of magnitude.
20 watts versus 50 gigawatt hours is an insane gap.
And that gap exists because silicon forces a separation between memory and processing. Every time data moves between RAM and the processor, energy is wasted. In a molecular system where computation and memory are the same physical process in the same material, that data movement disappears.
So when do we see this in actual products?
Molecular computing has been 10 years away for 50 years, so I'll be honest about timelines, but this paper is different because of the predictive theory. Previous molecular electronics research was trial and error, build something, see what happens. Now there's a design framework. You can engineer specific behaviors from first principles. That's the difference between alchemy and chemistry. The IISc team has a clear path to silicon integration, and they're actively pursuing it.
From alchemy to chemistry. If they pull it off, the silicon age might actually have an end date.
And the molecular age would be the first time in computing history where the hardware itself is as flexible as the software running on it.